Hey, welcome. This one is from GATE 2001 exam. It's a 2 marks question and is a easy one. Believe me, it's very easy question. So the statement says, consider the following data path of a simple non-pipelined CPU. The registers A, B, A1, A2, MDR, the bus and ALU are 8 bits wide. SP and MAR are 16-bit registers. The mux is of size 8 cross 2 ratio 1 and DEMUX is of size 8 cross 1 ratio 2. Each memory operation takes 2 CPU clock cycles and uses MAR and MDR. SP can be decremented locally. Then you have this diagram. The question reads, the CPU instruction push R, where R is equal to A or B, has the specification save R into memory of SP and decrement SP. How many clock cycles are required to execute the push R instruction? Okay. So first of all, I'm going to take 3 to 5 minutes to explain this diagram a bit. Okay, so bear with me. Anyways, I can tell you, no one is explaining such things for free on YouTube. Okay, let's analyze this diagram. Now, you're given that every register A, B, A1, A2, ALU and the bus, these are 8 bits. That means whatever data you are working with is a 8-bit data. So probably your memory is also 8-bit. Say this is your RAM. Now, what this question implies is each location is 8-bit. That location is a 8-bit location, which is probably true. We cannot be very sure it's 8-bit, but it's probably true because all the GPRs and the SPRs, that is general purpose registers and special purpose registers, they are 8-bit. That means whatever data we are working with, our operands, they are also 8 bits. Secondly, the bus is 8-bit. This is a 8-bit bus, which is given in the question. Thirdly, the ALU is 8-bit. Okay, this is also given in the question. Now what's up with these two registers? Why are they 16-bit? First of all, MAR is for memory address register. This is a 16-bit register. That means our memory address is a 16-bit value. Okay, so what it means is, first of all, these locations, all these are 8-bit. That means it can contain a 8-bit data. Second thing is, to select one of these locations, that means to fetch one particular address, we need a 16-bit value. Okay. So this 16-bit value or 16-bit address implies that total memory supported is 64 KB. How did I get 64? 2 power 16 can be written as 2 power 6 times 2 power 10 because 16-bit address means total 2 power 64 locations can be addressed. So the memory supported is 64 KB, assuming one word is equal to 1 byte. Okay. Next things that you can notice from this diagram is these registers, they have only a unidirectional bus. That means the stack pointer and the memory address registers stack pointer can only write data onto this bus. Memory address register can only read data from this bus. Notice these arrows. Okay. Let's try to find out a reason for this bus being unidirectional. You can see here the bus is bidirectional. We can read as well as write on this register A. But here it's not the case. You see, this mux only writes data onto the bus. It's so because stack pointer generally provides its value to the memory address register. So the data flows like this. Now why does stack pointer provides data only to this register? It's so because stack pointer contains top of the stack, okay, and top of the stack is a memory address. So only place where this memory address can be transferred to is a memory address register, because this register is directly connected to the memory. Okay, it's a 8-bit bus. This one is a 8-bit bus. This is a 8-bit bus and is the address bus. That means whenever we want to access some memory location, we'll save its address here. Okay. Now we will save its address here means the processor is going to save the address here. Okay. That means the bus direction must be this side, which is the case here. And second thing is, whenever this contains the address, we don't want to know that address. We actually want to access that address or access that location. That means it doesn't make sense to have a bidirectional bus. No, it's very obvious that memory is not going to tell us the address. We are going to tell the address to the memory. So data doesn't flow this way. Okay, this is wrong. Data doesn't flow this way means it also doesn't flow this way. Okay. Now next things that you can notice from this bus or this diagram is these registers. They are also unidirectional. First of all, these are special purpose registers. That means the programmer or the user is not allowed to use these two. Why? Because these are a temporary buffer for the ALU. That means whenever you want to add two numbers or subtract two numbers or any ALU operation for that matter, the data is going to be saved here and here temporarily. Say you need to add A and B. You write add B comma A. That means add these two values and save the result in B. For that, you need to first bring these two values into these temporary registers. Second thing is, these values will be added by the ALU and the result will be moved into the B register. Okay. So these two registers are only for the ALU. That means they act as a temporary buffer to store our operands. Okay. That's what accumulators generally do. Anyways, let's see next points. Now let's say we want to access this memory location, the memory pointed by our stack pointer. So the steps that will take place or the steps that we are going to follow will be, first of all, this register is not at all connected to the memory. That means we cannot access the address without bringing this address into this memory address register, because this is the only register that's connected to the memory for providing address. So the first step must be bringing this value into this register. Okay. So this data will flow like this. Okay. A 16-bit value from stack pointer goes to a 16-bit memory address register. Then this memory address register, because it's connected to this memory, will select that location, whatever location is pointed by the address, and that value or that the data at that location will be fetched into memory data register. Or if we want to write to memory, then whatever is present in this memory data register will be saved into that location pointed by this address. Okay. Next thing is, what are these two MUX doing? Why do we have MUX here? MUX and a DEMUX. Okay. Because our bus is a 8-bit bus, so we simply can't transfer a 16-bit value. Okay. These 16 bits cannot go via a 8-bit bus. Okay. So 16-bit value needs to be broken into half. Okay. That means 8 bits will be transferred first, then 8 bits will be transferred in the next cycle. So 16-bit value for getting transferred needs 2 cycles because bus is 8-bit. Now what are these two MUX doing here? MUX and a DEMUX. You see, this is a 2:1 MUX. By the way, that's given 1:2 in the diagram. The diagram in question is incorrect. Anyways, they have mentioned in statement 2:1. That means statement is correct. The error is just in the diagram. So say this is a 16-bit register. To transfer this value via a 8-bit bus, we can use MUX here. Say these are MUX. All of these MUX are 2:1 MUX. Yeah. So the two input lines can be connected like this. That means odd positions are connected to the first input of MUX. This is position number 1, this is position number 3 and 5. Okay, so this way the odd positions are connected to the first input of MUX. Anyways, the thing is half of the bits are connected to first input and half of the bits are connected to the second input. Because there are total 16 locations, we require only 8 MUX to do so. That's what's mentioned in the question. 8 cross 2:1 MUX. That means 8 MUX where each MUX is of this size. Okay. So this is in diagram they have only shown 1 MUX. Actually these are 8 MUX. So not their intention is just to tell you that what size of MUX is being used. So they have not drawn 8 MUX here. Anyways, this is what is actually happening. Okay. So you see, if we try to select the first input of MUX, that means our select line here is 0. So this is the select line which is given to all the MUX. The select line is 0. That means bit number 1, 3, 5, 7, 9 will be selected. So the value in output of all these MUX will be the odd bit positions because each MUX is going to select its first input. So the odd bits will be transferred onto this bus. Parallelly, this DEMUX will transfer the value onto the corresponding positions only because this will take one bit as its input and will be giving 2 outputs. Okay, so what I am saying is the first bit from here will be transferred to the first location in memory address register. So what you can notice is in the first cycle we'll transfer these odd positions and in the second cycle we'll transfer these even positions. Actually we can't be very sure whether this is happening or not. Say what is happening is that's really dependent on the implementation. One other solution to this problem is you can have the 16-bit register and probably you are dividing it into half. So these 8 bits are being transferred in one go and next 8 bits are being transferred in one go. So to facilitate this operation, what we'll do is we'll take the first input of MUX and connect it here. Second MUX first input will be connected here. The third MUX first input will be connected here. Okay, so 8 MUX, all 8 MUX will have their first input connected to these 8 locations. Parallelly their second input, this input, I'll draw it with another color. This input, this one will be connected to the first location in the other half. Similarly, its second input will be connected here and so on. So I think you're getting the point. So the register will be divided into half. First half will be moved in the first cycle and second half will be moved in the second cycle. That's what MUX and DEMUX do. Okay. So I'm not going to explain this DEMUX operation. Anyways, that's very obvious. If you have studied DCLD or digital logic, you know how this is working. Okay. Now I think I've explained the diagram. Let's now see these two statements. Okay. This is now going to take only a few seconds. What we need to do is, we need to address this location pointed by SP. That means this value needs to be moved into memory address register. 2 cycles, that means T1 and T2. In T1 and T2, what we are doing is memory address register gets, I think it's not visible. Okay. Anyways, in first 2 cycles, this SP writes its value into this memory address register. Second thing is, now this R contains the value that needs to be saved into memory or into the top of the stack. That means R can be any of A or B. That means these values or any one of this value needs to be moved here. So it's going to take 1 cycle because both of these are 8 bits. Okay. So I'll write down the sequence here. T1 and T2. In these 2 cycles, what we are doing is we are saving address into memory address register. So SP's value moves here. In T3, what we are doing, we are saving this R in T3, this value, because it needs to be transferred to the memory, is saved into the memory data register, because this is the only register which is connected to the memory to transfer data. Okay, whether that transfer be from memory to this register or this register to the memory, that's the only location which is connected to the memory for the purpose of transferring data. Next thing that needs to be done is the value from this register MDR needs to be moved into memory. Okay, that's given as 2 cycles. So T4 and T5 is MDR to memory. That means this actual data transfer happens in last 2 cycles, which is T4 and T5. The next step is decrementing stack pointer. Stack pointer can be decremented locally. This is what is mentioned in the question. What it means is, decremented locally means we have a control signal which when high will decrement its value by 1. Decremented locally means we don't need to bring this value into the ALU and then decrement it and save it back again. So the hardware provides a support for decrementing value of this location. That means you don't need an extra clock cycle to decrement it. Decrementing SP means just generating one control signal, which is this DCR. Okay. So when we have used this value, that means once we know what is this value or we have saved this value here, we can decrement it at any time. That means either in T3 or in T4 or in T5, this value SP can be decremented. So these two operations can happen parallelly, because first operation takes these 3 cycles. First operation takes 5 cycles. Okay. And the second operation, decrementing SP, can happen anywhere from T3 to T5. Okay. So your answer to this question is 5 clock cycles. Let me see the options if 5 is present. Yeah, it's D part. So answer is D part, 5 clock cycles.